So this lecture may be thought of as introductory, and the two important points are, well, I guess there's three. There's the Jacobian matrix, its determinant, and the concept of differentiability. That's the nutshell of this lecture. All right, so what we're going to do is try to apply the explore the topics on the previous slide for general functions. Now, what do I mean by general functions? Well, you could say we've already been looking at general functions, and we have, but I mean really general functions. We've been looking at vector-valued functions of one variable. We've been looking at real-valued functions of 2 and 3 variables. Well, this section brings it all together. So, in section 2, we looked at these general vector-valued functions of one variable. So t is the independent variable. You plug in t and out pops a vector. And we then define its derivative by differentiating the components. So that's one way, well, I guess in that context, that's how you define the derivative. We've also looked at these functions of 2 and 3 variables, real valued functions. And we defined partial derivatives and directional derivatives and the gradient field. Now, as we'll see a little later, you can think of the derivative as the gradient. It's a bit more complicated than that, but for these functions, in this section, you can think of a derivative of a function as the gradient of that function. Okay? Now, how can we generalize these kinds of functions? Well, we can do it in the following way. What we're going to do is form a vector-valued function of many variables. So, we're combining the functions from section 2 and section 3 together. So they all come under one type of umbrella. So let me give you an example. I think there's an example down here. Aha, yes. In this example, we've got, and you know, look at how it's written as sort of columns here. Think of this as a vector in R cubed. So the independent variables are vector, x, y, z, in R cubed. And it outputs a vector in R squared. Okay? So x, y, and z are all real value. They're just numbers, right? But together, you've got some vector input and some vector output. This vector is 3-dimensional, this vector is 2-dimensional. So that's, we haven't really looked at those kind of functions before, not in any detail anyway. Now, if you look at the output, we've got, you can sort of think as the components, f sub 1 and f sub 2, the component functions as being real valued functions, and together, written as a vector, column vector, they make up some sort of vector output. Okay. What about a couple of other examples? So let's say I've got G defined in the following way. Okay, so for the example I've just written, G would map R squared into R squared. Okay, so more generally, you can sort of map Rm to Rn, where n's greater than 1, so it's a vector valued output. Now, you can sort of, some people write these the other way around. They have the n over here and the m over here, but I'm just doing it because m comes before n in the alphabet, right? Okay, there's no like golden sort of deep thing there. What about, oh yes, what about another one? Okay, let's say I've got J and it's defined in the following way. Look familiar? Now if I sort of denote the output of this as, say, xy, well, what we're doing with that bottom vector function is I'm transforming, I guess, from, I guess our transformation involves polar coordinates. And we're mapping, I guess, with this sort of label into the xy plane. Now we'll look at that in a bit more detail in a bit later, so just bear with me. In this section, we really should write vectors as column vectors. And I've sort of been switching between the two in the previous sections. And the reason why it's important in this section is because when we define differentiability, we're going to use this Jacobian matrix, and it's going to multiply through by a vector. So if you've got a matrix times a vector, it's easily evaluated if you write your vector as a column vector. Okay, so this is probably the best notation, but I'm pretty flexible with that. I'm not going to tell you exactly how to do it. As long as you're consistent, I'm happy. Okay, again, the F1 and the F2 here are just real valued component functions. Okay, so if you look back at the example 1, these functions, F1 and F2, for this particular example, they're just real valued functions of 3 variables. We call them the component functions or the coordinate functions. And that's the kind of language I've been using throughout this course. So, generally, if you have some vector valued function of m variables, you can, if you want to determine it, you can just write it as this sort of column vector with f1, f2, etc., all just real valued functions of m variables. Now, don't be too put off by this. The most important cases are when we map between R2 and R2 and R3 and R3. Okay, so don't worry too much about the sort of abstractness of this at the moment. Oh yes, there we go. Yes. Now, our interest in these two cases lie, I guess, for 2 reasons. Firstly, this is where the most physical applications occur. And secondly, especially in the case where f maps r squared to r squared, this is going to be very important when you guys do integration. So in the second half of this course, you guys are going to look at integrating over regions like 2-dimensional, 3-dimensional regions. And this is going to be important. Okay, is this case here. So again, you can use this type of notation. Now, so one of the really difficult things with these kind of really general functions is to visualize what they do. Okay, functions of one variable, just real valued functions, are not too bad. We can just draw a graph or something. But with these very general functions, it's more difficult. Now, what you can do is think of this function f as sort of mapping between 2 sets of coordinate planes. Okay, so you've got points here. So think of this as maybe as a domain of f. So for each x, y, you've got some sort of position vector associated with it. F takes that position vector, transforms it to a new plane, and you get a new vector. But even that's pretty hard to visualize, okay? But at least from that sort of rough outline, you get an idea of what's happening, hopefully. Now, depending on what the vector-valued function is, it may do certain things to its domain. It could stretch it, it could compress it, it might rotate it. And this kind of, I guess, visualization is going to be really important when you do functions, integration of in sort of Rsquared and things like this. Change of variables in multiple integration. So it's going to be quite important. Now, in this setting, you would sort of have, okay, well, u and v as just f of x, y. But you can have it the other way around. U and v could be the independent variable, and you could map from the uv plane into the xy plane. Sometimes that happens as well. I guess swapped. But by swapped, I mean reversed here. So, you might have this. Say, okay, so this might be your domain, and you're sort of mapping into the xy plane. All right, so remember we're doing a course on several variable and vector calculus, right? And we've been looking at derivatives all the way through. So let's try to define what we mean by derivative of this very general type of function. What does that mean? Well, let's try to build our intuition a bit. How do we define a derivative of this very general case? Now, what we would like that derivative to do is to do things that we know for the basic sort of high school and first year math. Like, if we're going to define a derivative, we want sort of theorems to work like, differentiability implies continuity. Things like that. Okay, so whatever definition we're going to pick, we want it to be sort of a natural generalization of what we already know. Now, in the section 3, we looked at a directional derivative where this u some unit vector. And in particular, from this, we see that knowledge of the gradient of f gives us information about all the directional derivatives. And based on this assumption, it's reasonable to assume that the gradient of f evaluated at p is the derivative of f. Now this is just say in this example, a function of two variables, right? So that's kind of a little leap. So this is for a function of two variables, a real valued function. What happens if I have a function of, say, m variables? So instead of the variables being x, y, z, what happens if they're x1, x2, x3, blah, 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 x sub m? Well, you can still look at the gradient of f, and we're going to define the derivative of this function, real valued function of m variables, just to be the gradient. of f at this point associated with the vector p. Now, what happens if I've got a vector, a general vector valued function of m variables? So here, I've got something like, f1, f2, blah, 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 fn. Well, if I cover this up, I've got the case up here. So what I'm going to do, gradient of f sub 1 and write it as a row. Then I'm going to go down to f sub 2. Take the gradient of f sub 2 and write that as a row. And then I'm going to keep on going until I get down to f sub m and write the gradient of that as a row. So this is just a matrix that has rows which are just the gradient of the component functions. Now that's a lot to take in. But hopefully you can see where this is being built from. It's just sort of built around this, really. So, instead of just one function, you've got all these other sort of component functions. And we call this matrix the Jacobian, named after a mathematician and physicist, I think, Jacobi, right? Yeah. So note the notation. This capital J with F just means the general Jacobian. If you put this subscript P in, it means that we're evaluating the Jacobian at the point associated with the vector P. Okay? Now, sometimes what people when they mention the Jacobian and nothing else, what they really mean is the determinant of that big matrix. Okay, so it's important that you sort of distinguish between the two. All right, let's do an example. Okay, find the Jacobian of the Jacobian matrix of F from example 1. So let's just remind ourselves what the actual function is. And we're asked to evaluate the Jacobian matrix at the point, I guess, 1, 2, 3. Okay, so over here we've got, F1, F2, where both of these component functions depend on X, Y, and Z. Okay, so essentially I just go to the first component function, calculate the gradient, and write it as a row. So in terms of partials, it's going to be something like this. Okay, so now let's move on and write down the gradient of the coordinate function f sub 2 and write that as a row. Okay, so I'm going to get 1, 1, 1, yz, xz, and xy. Okay, so more computational than anything, just designed to get you really trying to remember the Jacobian. You won't get the Jacobian format given to you in the exam, so you'll need to be able to recall it. So let's call this, I don't know, the vector associated with this point. So all we're doing now is evaluating this at the point 1, 2, 3, really. So if I sub in, x equals 1, y equals 2, z equals 3, I should get something like this. Okay, so if you can take partial derivatives, or you know the gradient, no problem. Anyone still going? Now, most of the cases we'll be interested in is when m is equal to 2, m and n are equal, and they're both either 2 or 3. Okay, this should be boldface there. So if you've kind of got these independent variables x and y, and you've got functions here, u and v, then you can write down the Jacobian matrix. Now, a very important aspect of the case when we have a squared Jacobian matrix is the determinant. And this is important for all sorts of reasons, and we'll discuss a couple of them. Note the two potential styles of notation. The benefit with this is that it's very clear what you actually mean, right? And with this one, I guess one of the advantages is you have some idea of the differentiations involved. So you can sort of, write down this and still understand the Jacobian associated with it. So I guess both of these are acceptable, but you both need to be aware of both of the styles of notation. Okay, you may see both on your exam. Okay, so let's look at another example. So this one involves polar coordinates. So essentially, we are, okay, I'll use air. So in this context, we've got this vector valued function of two variables, this f, if I write it in this sort of column vector format, this is what we have. Now, if we wanted to write down the Jacobian, well, you can do that. You just sort of, I guess this is sort of the you just take out these sort of determinant lines here. Okay. In this case, we have a square matrix, so we can calculate the determinant, and if you just, expanding through the normal ways, you get the determinant to be R. Now let's put this into a little bit more of a context. Let's actually have a look at what this sort of mapping does here. Suppose I'm working in the r theta coordinate plane, and I've just indicated this little sort of filled in square. F picks up on this and maps it into the xy plane. Actually, let's make that pi on 2. Yeah, that's better. Anybody know what kind of shape we're going to get in the xy plane? What sort of what are we going to get when f sort of acts on that little rectangle? Any idea? Yeah. Yeah. Well, I guess what you're going to get is sort of a quarter of a disc. So hopefully you can see that, all right, in this particular example, the f sort of takes this, you've got sort of 4 sides, one of them sort of bent or curved, one of them shrunk down to a point, and this is of course going to influence the shape of the output of our f. Okay, so this is going to be quite important when you're looking at integration. And let me tell you why, without going into too much integration. Suppose I've got a really awful region that I want to integrate over. Wouldn't it be better to work in a simple region and do your integrations there? Yeah, sounds reasonable. This is exactly what you're going to do, and it's going to involve the Jacobian and its determinant, the Jacobian matrix and its determinant. Okay. Let's look at another example. A good question here is, okay, well, so what? So, all right, I understand the Jacobian a little bit. That's kind of like a derivative. But what does the determinant mean? Well, I'm glad you asked. Let me show you. Here's another little example that I'll squeeze in here. What have I used? T. Okay, so this is a real simple function. So this is nothing here. Now let's calculate the determinant. The Jacobian and its determinant, right? So if I go through, I'll get something like this. Okay, pretty simple. And now, let's look at the determinant of this Jacobian. Ran the wrong way. Okay, so the determinant's going to be 6. So what does it mean? Anyone know? Yeah. Well, I guess it's hard to talk about the gradient because we've got a vector valued function of many variables. But I'm just even thinking, even simpler than that, I guess, and similar to this kind of diagram over here, let's just draw in another, so this is the, let's say U and V, right? Under the transformation, what happens? Well, this goes out to 2, and this goes off to 3. Okay, badly drawn, but hopefully you get the idea. So what's the area of the first box? 1. What's the area of the second box? 6. Have a look at the determinant. Also 6. So in that sense, what we might conject is that this determinant of this special Jacobian matrix, it's like a scaling factor for the functions involved. In this case, the sort of area box area 1 is sort of increased by a factor of 6. This is actually true in general. So this has area 1, area 6. So it's like a, you can think of the determinant, the Jacobian determinant as like a scaling factor. It might decrease the thing. In that case, it'd be something like a half, something like that. Yes? Sorry? Because I'm choosing it to be that. Okay? Yeah, I'm just restricting the, I'm just choosing a simple sort of domain that suits my purposes. Okay? All right. So this is important, okay, when you look at double integration. So when you come back to it, hopefully you won't be too stunned. Yes? Depends with what you're differentiating with respect to. Okay? So don't, like, that's one of the biggest mistakes students make, is that they concentrate on the formulas rather than the variables at hand. Okay? So yes. So my advice is not to do that. All right, on to differentiability. What do we mean when we say differentiable? Now, first of all, let's motivate the idea first, because there's a lot to take in on this slide, I've got to admit. Just about every concept we've dealt with in the last 4 weeks has involved an assumption of differentiability. Has anyone noticed that? Assume f is differentiable, assume this is differentiable, assume this and this is differentiable. Differentiability is very important, because if we know we have a differentiable function, we can do lots of things with it. That's the key. All right. Once we have, so suppose we have a function, general function. Once we have the Jacobian at some point A, we can define this linear map just through matrix multiplication with a vector. Okay, now it might be a vector. The Jacobian might be a vector, so you might actually be multiplying 2 vectors there. That's why I put the dot in. Now, when we say that a function f is differentiable at Q, the same ideas apply as we saw in section 3. Basically, it says that there is an affine function that is a good approximation to f near the point of interest. Now, the affine function, remember, an affine function just has a linear part plus some sort of value or constant. So what do we mean when we say this affine function is a good approximation to f near the point? Well, we define it to be this way. Now this is much like a step up from what we saw in section 3, but the ideas are pretty much the same. Just think of, this is a distance, and roughly this top bit as a distance as well. Now this is a lot to take in. I don't expect you to, just to get that straight away. But the concepts are the same. They haven't changed since section 3. It's just we're dealing with more general functions. So let me show you a very convenient theorem. And this is important from a practical point of view. How do we easily recognize a differentiable function? I don't want to sort of look at that if I don't have to, right? Well, if all the components of the Jacobian matrix associated with that function are continuous, in other words, all the partial derivatives are continuous, then the function is differentiable in the sense of the previous slide. That is a huge result that you can use all the time, almost, as long as the conditions are satisfied. So let's do an example. So this is like, this is gold. Okay, really happy. So from a practical point of view, this theorem is fantastic. So let's just squeeze in a little example here. Okay, well, let's compute the Jacobian and look at its elements. All right, so if I compute the Jacobian, I'm going to get 2, 1, minus 1, and 2y. Now, let's look at the elements, or the components, I guess, or the elements of the Jacobian function. Are they all continuous functions? Yeah, well, constant functions are continuous, so they're all right. 2y, of course, that's continuous everywhere. So, from the above, we will conclude that this function everywhere. Now that's what we want you to know, okay? From a practical point of view, we want you to know that if the Jacobian matrix has continuous elements, then the original function is differentiable. We want you to be able to appreciate what's going on the other slide, but I would never ask you to reproduce it. Yes? No. That's a good question. But no, so it's an if-then statement. Sufficient, not necessary. Okay, good stuff, really good stuff. That's stuff you can use. Okay, last question, last example. Write the derivative of the function in example 1 as a linear map. Okay, so we calculated the Jacobian at the point of interest to be this. So how do we set up this linear map that we sort of looked at a couple of slides ago? Well, it's just matrix multiplication with a vector. So it's pretty easy once you know how. Okay, linear map involving a matrix involves matrix multiplication with a vector. Okay? Now, if this Jacobian is some sort of derivative, then what are the rules? What about, if I add two functions together, is the Jacobian of their sum equal to the sum of the Jacobians? Yes. And you can the general rules of calculus apply. So sort of the algebraic type rules here. Now, you can also take the dot product of two vector valued functions of many variables and differentiate that and get some sort of product rule. But I'll leave you to work out what happens in that case. There's no quotient rule because we can't really divide vectors by, a vector by another one. So that leaves the chain rule. We'll look at that on Monday.